Hi, everybody. So I'm Nicola Mometto. You might know me by my nickname, Bronza. I've written a bunch of libraries, which you might have heard of, called Tools Analyzer or Tools Reader. But yeah, today I'm going to talk to you about a new library that I've been working on called tools.decompiler, which, as the name suggests, is a decompiler for Clojure. But first, a quick overview of how compilation actually works in Clojure. So we have the simple steps of reading, which is taking a stream of text and turning it to code as data. Then we have a step, which is macro expansion, which takes this code and completely macro expands it. We have an analyzer that takes that macro expanded code and turns it into an AST. And usually, in the implementation, the macro expansion and the analysis are done in lockstep, but that is just usually a performance optimization. So we can think of them as separate phases. And finally, we have an emitter that goes to AST to actual bytecode, which the JVM executes. So those are the basic steps, and keep them in mind because for decompiling, we're just essentially going to run this pipeline in reverse. A quick overview of the class file structure. So everything that runs on the JVM has this class file structure. A class file has three different aspects to it. It's got a constant pool where the JVM stores stuff like string constants or integers or references to classes and methods. It's got a list of fields, of static and instance fields. And finally, it's got a section which represents the method bodies of this class. And so those method bodies have some quite interesting properties, and they're very rich in what they contain. And they have a lot of debug information which helpfully the Clojure compiler emits, such as the local variable table, which gives you a set of local names to offsets in the bytecode, which the JVM uses for printing useful debug information in stacktraces. We have an exception table which tells us the bytecode offsets where an exception handler will be active. And we have a line number table which tells us which bytecode offsets map to which code line and columns. And finally, we have the proper bytecode. So with that in mind, the architecture of the decompiler is this. We have a bit more phases than what I previously described, but it's pretty similar. So we have initially a bytecode loader, which takes a byte buffer or a byte array and returns that represents bytecode and returns the same bytecode in a symbolic form so that we can manipulate it as if it was data. We have then an analyzer that takes this data structure representing the bytecode and turns it into a AST, which is also data. We have a Sweetener, which is a phase that takes AST and returns AST, but does some sugaring over that AST. Then we have a compiler that takes this AST and turns it back into Clojure code. We have a compactor that takes this code and tries to reduce the amount of code that we have to undo macro expansion, for example, and undo inlining. And finally, we have a preprinter that takes this code and just formats it and makes it a bit more readable. So let's go into all these phases in a bit more detail. The bytecode loader is implemented using BCL, which is an Apache library, which is quite similar to ASM, only it's got a more horrific API, but it's got a much better support for actually parsing bytecode. So what the bytecode loader does is it starts parsing this bytecode, and it parses the class fields first, so that we can have a representation of every data field in our class. And then we start parsing all the methods and building in memory all those debug tables that we're going to use. So we build the exception table, we build the local variable table, and we build this jump table, which is going to be a mapping from bytecode offset to positional elements in this bytecode vector, in this symbolic vector, which we're going to use to map jump instructions when we're going to decompile. And then we're just going to build this symbolic bytecode vector and just going to represent the bytecode as a data structure. And this is what a class for just returning a string hello looks like. And if you've ever used a library called no-disassemble, you're going to see that it's quite similar. It's not exactly the same, just because for decompilation purposes we needed a bit more information, but it's close enough. Then we have the analyzer that takes this data structure and tries to turn this from bytecode to an ASC representing Clojure code. And so the first thing that the analyzer does is it needs to figure out what type of class we're actually trying to decompile. So the Clojure compiler emits 3 different types of class files, 4 actually. So we use some heuristics to figure out which class file we're looking at. So if the superclass of this class file is AFN or RESTFN, then we know that we're decompiling a Clojure function. If the class file implements itype or iRecord, then we know that we're decompiling a def type or a def record expression. And if the class file, failing that, if the class file implements iObject and the name contains refi, then that's the only way that we have to know that we're trying to decompile a refi expression. And finally, if all this fails and the name of the class file finishes with -- init, then we know that the class file that we're trying to decompile is a namespace initializer that contains all the mapping in that namespace to all the functions that are defined. After this dispatch, the analyzer does some analysis over the methods, and it needs to ignore methods that we don't care about, that are just emitted for JVM running purposes, such as abstract methods or bridge methods. We then initialize static fields by parsing the static initializer. And then we collect all the useful methods to decompile. So in the case of a function, we're going to either collect invoke methods or invoke preim or invoke static methods, depending on which one the function actually implements. In the case of namespace initializer, we're going to collect the load method, which is what the Clojure compiler emits, and so on. And then we're going to start processing each method, and we're going to start decompiling it. And to do this, we're going to use a stack machine interpreter, which rather than executing proper instruction, just builds AST nodes. And it does so by using a bunch of virtual stacks. So it operates on a virtual stack. And rather than properly executing instruction, it just pushes AST nodes into this stack, and it just operates on that. And we have a PC to track which point in the bytecode we're at. And so this processing of instruction is a bit different in the case of different instruction types. So for stack operations like swap or dump, we execute them as if it was a real virtual machine. So we take the value that's on the top of the stack and we just replace it. For branch operations like instance of or IFIC, we know that this means that we're at the starting point of a conditional expression in Clojure, like an if or a case statement. So that's going to help us know that we're going to have to produce an AST node representing that. If we encounter local variable operations like a load or a store, then we know that we are at a point where we're starting a lexical block, which might be a let expression or a loop expression, and we're going to have to do some analysis to figure out which one it is. And so on for math operation and every other invoke operation, we're just going to create the appropriate AST node. So those are examples of methods that process those instructions. So we see for the dupe bytecode, we just pick the value of the virtual stack and just update this stack, adding the same value on top of this stack. For the operation that does get static, which maps to a static access field, we retrieve the target class and the target name out of the pool element. And we just generate this map op static field, which represent this static field access. And we just push that onto the virtual stack. Another example is this ifec processing instruction. And so in this case, all that we do is we collect the offsets in the bytecode that map to the true branch and the false branch. And the test case is going to be the value on top of the stack. And after we've collected all this, we just pass this information to a processive function that just takes the starting and ending offsets of the then and s branches and decompiles those branches as if they were normal control flow operation and just builds an appropriate AST node. And so this is what the AST kind of looks like for that same expression that I've shown you before. And if you've ever looked at Tools Analyzer or the ClojureScript compiler, you're going to see that the AST format is exactly the same. And this is going to be important later. The Sweetener is a phase that essentially adds syntax sugar over the AST, and it overlaps significantly with a later phase that I'm going to describe, which is the compactor. The way in that they differ is that the Sweetener acts over the AST while the compactor acts over code. And so if you have to do some sugaring that needs to know type info, for example, or lexical context info, then you're going to have to do it at the AST level. Decompiler is a really simple phase that takes AST and outputs Clojure code, and it's essentially the same code that Tools Analyzer uses and that CoreAsync uses as well. And this is really, really important because by reusing the same code, we're building on top of a code base that have been proven correct for a couple of years. And a very interesting phase now is the macrocompaction, which needs to undo macro expansion and undo inlining. And if you know a bit about macro expansion, you're going to know that it's technically impossible to undo it because it's a problem equal to solving the halting problem. So what we do instead, rather than trying to solve an impossible to solve problem, is we use some heuristics and pattern matching to undo this in a best case way. And so when I was trying to implement this at first, I thought, well, we already have Kibit that does something like this. It recognizes patterns and tries to suggest more abstract representation of them. And I've implemented a first pass using Kibit and core logic. And it worked beautifully. The problem is that it took 15 seconds to macrocompact a simple do-seek expression. So it wasn't really viable. And on top of this, by using core logic, we will lose the ordering guarantees because it's a relational engine. And it turns out that we actually need ordering guarantees because macro expansion is defined in a specific order, and we need to undo it in exactly the reverse order. So the second pass of this compactor was written with core match. And it was really, really fast. I've written a DSL over match because if you've ever tried to use core match to pattern match over structural data, it's not very pleasant. So I've written a DSL that kind of looks like structural matching. The problem with using core match is that we lose the guarantees of unification. Oops. Of unification. But for the use case that we need, it turns out that we can simply use guards to enforce the quality guarantees that we need. And so this is what the DSL kind of looks like. And this is the compactor for end, the end macro. And what this is doing is saying if my expression starts with a let and then a t symbol that maps to a x initialized value, and if the children expression is an if statement in which those terms appear, and if t is a symbol that starts with end underscore underscore, then this is a good match for an end expression, and compact is going to replace this let if expression with the end expression. And so this is a simple expression. This is a simple example, but this is powerful enough to compact almost every macro in Clojure core. After the compactor, we have a pretty printer, which just takes care of removing some boilerplate that the Clojure compiler emits that's not part of the original source code. And it does stuff like editing namespaces and using aliases rather than long namespaces. And it uses FIP to pretty print, which is really, really fast and really good. And so at this point, after writing all this, I had a working decompiler. And so if you've ever written a compiler or an interpreter, a self-hosting compiler, then you know that the first thing that you're going to do is point it at itself. And so I did. And I got this. But this happened not while trying to decompile the tools decompiler. It happened while trying to compile it. And as it turns out, the compact macro that I wrote was causing so much code to be generated that the file name was too long for the file system to handle. And so what I did initially was to try to work around this by patching the compiler.java to make it so that the file name got truncated. And it worked. And by it worked, I mean nothing worked for 3 days. And I fixed hundreds of bugs, and then it worked. And the problem was that I noticed that my legs were frying because one thread, one CPU was stuck at 100% usage. And so I didn't know what's going on. And I knew that my code wasn't responsible for this. So I looked at the dependencies that we're using. And it wasn't BCL, it wasn't core match, and it wasn't FIP either. So I turned to the one remaining thing, which was the Clojure compiler. And after hours of debugging, it turned out that the Clojure compiler wasn't at fault either. And so this is a picture of me at 3 a.m. that my flatmate took. And I had no idea what was going on, honestly. And it took me a couple of days, and I finally noticed that this only happened while trying to decompile the decompiler itself, or while trying to decompile very large programs. If I was decompiling simple functions, then it worked fine. And so I got this idea. It kind of felt like it must be something that happens while some instruction gets executed multiple times. And so I thought, well, maybe it's the JVM itself that's causing this. And so I took thread dumps of the JVM processes. And yeah, it was the C1 hotspot compiler that got stuck in a busy loop. And this happened because the way that core match emits in the way core match compiles match expression, it uses a lot of exception to backtrack, and in a way that apparently the JVM that puts the JVM compiler in an exponential loop. And so I was at a point where this compactor was causing me to have to patch compiler and causing this bug in Hotspot itself. So I decided that I needed to fix this in a proper way. And what really helped me was that core match is a beautiful library, and it's implemented as a proper compiler. So it's got a separate front end and a separate back end. And so I decided that a way to fix this would be to just change how the pattern match is emitted as Clojure code. And so I wrote a new backend for core match that uses continuations rather than exception for backtracking. And this fixed all the issues because now I didn't have nested, like hundreds of nested functions. I just had a flat list of continuations. And the JVM hotspot wasn't unhappy about it anymore. And it turns out that when you're doing matching over a massive data structure, then this is also way faster than using exceptions. And so, yeah, I was really happy. I had a working prototype. And I'm going to show you now what that looks like. So here I'm just going to import some stuff. And I have this foo definition, which is, I have no idea what it does. I just wrote it to be as complex as possible. And so this has a lot of complex destructuring, a number of very complex macros and I'll show you what the macro expansion actually looks like. So for that 8 lines of code, this is what the compiler sees. And this is what I'm going to try to make look similar to the original expression. So I'm going to evaluate this function, and I'm going to invoke this decompile classes method on the decompiler. And there we go. So I'm going to indent this a bit so you can look at it. And as you can see, this is almost exactly the same code that we had originally. And you can tell that I'm not cheating because F and G have extra parentheses. And so this is really cool for me. But what are some practical consequences of having this type of stuff? So an idea that I had, because of the property that the decompiler goes through an AST that's the same format as tools analyzer, I thought, why can't I just decompile to AST and then pass that AST to tools analyzer and do some phases over that AST and recompile it? So that's what I did. This is a proof of concept of a spybang macro that takes an in-memory function and adds debug information to it without ever looking at the proper source code. So I'm going to just define this helper function. And we have this makeinspect node, which is taking a form and an init AST node and just inlines this handwritten AST node that builds a debug information node. I'm not going to describe what it does. You can look at it later. And then we have this spybang function that takes a var and derefs it, gets the class name, decompiles this function until AST, runs this tools analyzer pass over this AST. And what this does is it looks at the current node. If the current node is a let binding, then it replaces the initialization of that init binding with the AST node that I've just shown you before. Otherwise, it just keeps traversing the tree. And after this is done, we just take the AST and we compile it back to Clojure. We evaluate it, and we rebind the original var to this new version of the function. And so let's take, for example, this bar function, which has 2 let bindings, and invoke spy on it, and invoke bar. And so what this is doing is injecting code without ever looking at the source code. And this might seem trivial, but it's a really interesting way of doing metaprogramming. So a few ideas that I had for this approach would be to having a compiled function, making it go from synchronous to asynchronous without ever touching the code. Just taking a var and saying, hey, I want this function to be async now. well, let's just decompile it and then rewrite the AST node and recompile it on the fly. Or stuff like, how many times have you had a stack trace? You got anonymous function can be cast to whatever, and you have no idea what that anonymous function does. Yeah. What if you could just click on that anonymous function and get the source code? How good would that be? How good of an experience would that be? Oops. And so this works quite well. There are some known limitations. So the Clojure compiler does some munging on the names, and we have no way of knowing what the original names were. So if you have A-B, we're going to decompile it as A_B, because we have no way of knowing whether the original name was A_B or A-B. This means that there are some cases where symbol might collide, and we have no way of solving this. At the moment, we don't emit type hints at all, but it's something that I'm looking to doing. If the original source code contains explicit casts or implicit casts, then it's possible that the decompiled code will either contain extra casts that are still technically correct, but that it's going to be a bit more code than in the original source code. There's a few macros in Clojure code that I haven't written a parser for. But that's just a matter of doing it. I just got tired of writing parsers. And there's a known bug in which, so the Clojure compiler will happily emit bytecode that's technically wrong, just in ways that the JVM will never reach. So the JVM doesn't complain about it because it's unreachable. The compiler doesn't know that when an instruction is unreachable, so if that's the case, it might barf. It will only happen in very, very hard to find edge cases. I've only had it happen once. Some future work, I want to try to sugar syntax quote expression. So if you've ever looked at what syntax quote emits, it's a massive amount of apply and list and concat expressions, which at the moment are just in lines as if they are. I want to write a parser that figures out whether this amount of code is a syntax quote expression and print it easily. Support for macros like for and doseek is there, but I don't support when and let in for and doseek, because it turns out that it's really, really hard to parse that. And NS is not compacted because the output code is readable enough, but it's something that I'm looking to do in the future. And another interesting thing to do maybe is to use the line table to guide proper p-printing, which is something that I'm not doing at the moment. And so I wanted to open source this, and I wanted to open source this today, but I thought I'm going to have some fun with you. And so I'm going to open source this evening. But in the meantime, you can go to this URL instead. And what you're going to find there is a jar file with the decompiler AOT compiled, which you can use to decompile itself and look at the code. And so that's all I had for you. Thank you.